Hello guys, today we're going to prove that root 2 is irrational. So to do this, we're going to use a proof by contradiction method. So to do that, what we're going to do first is assume that root 2 is rational. We're going to say assume root 2 is rational. So you might recall, if you were watching the video, what this means is, what root 2 is rational means is that root 2 can be written as a divided by b for some a in the integers and b in the integers, and well, that's the additional condition that b is not 0, because we should not have divided by 0 here. And another thing is that a and b should not have any common factors, because I could write, let's say 3, I could write 3 as 6 divided by 6. 18 divided by 6, 18 divided by 6. But here between these two numbers there is a common factor which I can cancel out, and I can say this is equal to 3 divided by 1, or let's say 2/3 or some number like that. I could write 2/3, right? This number which I call 2/3 could have been written as let's say 18 divided by 27. But there is a common factor here which could have been erased to give us a simpler number. So this should eventually end up with the simplest possible ratio of two integers to give us the equivalent number. So I'm assuming that that's the case for root 2. For root 2 there are some two numbers where when we divide one number by the other we get root 2, and both of these numbers do not have any common factors. So I'm going to say that as an assumption, a and b don't have any common factors. It's called co-prime, but for now I'll just say do not have any common factors. So we're going to call this number 1. This is statement number 1, which we're going to use later. So this is the assumption we're making. We're assuming that root 2 can be written as a divided by b for some a in the integers, b in the integers, and b not 0, where a and b do not have any common factors. So we already assumed that this is the case. Then we can write that root 2 is a divided by b, which then gives us that a is b times root 2. So this is a true statement. There's nothing wrong here. We're going to call this 2. Now we're going to take 2 and we're going to square both sides. So from 2, by squaring both sides, we get that a squared is equal to root 2 squared is 2 times b squared. This is of course true. This is definitely true, because if we have one LHS is equal to RHS, then we can guarantee that LHS squared is equal to RHS squared. We cannot go in the reverse direction of course, but we can at least do it in the forward direction, which is why this is not this symbol. This symbol means I can go in the forward direction and reverse direction. This symbol means I can only go in the forward direction, or at least I'm only considering going in the forward direction. So now we have this. We have a squared is equal to 2b squared. Now notice, because b was an integer, b squared is also an integer. This is an element of the integers. So then we have that a squared is 2 times an integer. A squared is 2 times an integer. Therefore, we can say a squared is even. Right? I hope there's no issues with this, because b squared is an integer, and because we define an even integer to be a multiple of 2, as in 2 times some other integer, we can say that a squared is even. And this also implies that a is even. How does it imply that a is even? Well, in the case that a is odd, a would be of the form 2n plus 1. A would be of the form 2n plus 1. So if this is the case, then we can say that a squared would be 2n squared, which is 4n squared, plus double of 2n, which is 4n plus 1. Now here this n squared is an integer, because originally remember this n was also an integer. So n squared is an integer, this is an integer, so this whole thing is even. An even number, because it's multiplied by 4. An even number plus 1 is an odd number. So if a was odd, then a squared would also be odd. and the only way that a squared is even is if a was also even. I hope there's no issues with that. It's pretty clear if you think about it. So that means that a is even. So now that we have that a is even, we can also say that a is 2k for some k in the integers. This is of course the case because that's literally what even means. Even means that the number is 2 times some other integer, and that is what we have here. So I've defined some k, and a is 2 times that k for that integer k. Now we're going to call this number 3 and go back. We're going to go back to, actually we'll call this number 4 and we'll call this number 3, and then we'll go back to 3 using 4. So from 3 and 4, what we derive is, right, from 3 and 4, if we substitute 4 into 3, what we get is that 2k squared, replacing a with 2k squared is 2b squared. So we get 4 times k squared is 2 times b squared. Now notice if we divide both sides by 2, we get that b squared equals 2k squared, and since k squared is an integer, this is an element of the integers, this gives us that b squared is also an integer, right? So b squared is an even integer. B squared is I should say is even by this fact, by the fact that b squared is 2 times some integer, b squared is even. But now notice we have a similar thing to what we found earlier. Earlier we found that a squared has to be even. Now we found that b squared is even. By the same logic, we can also say that b is even. By the same logic, we say b is even, and therefore we can say again by a similar method, b is 2, I'll call this a different symbol, let's say k, we'll call this L, 2L for some L element of the integers. We'll call this 5. So now we've proven that a is an even number, so a is 2k for some integer k, and we've also proven that b is an even number, so b is 2l for some integer l. But now we have a problem. From 4 and 5, we can see that a and b have a common factor of 2. We can see that because here we can see a is 2 times an integer and b is also 2 times an integer, which, if you recall, should not have happened. From over here we said that a and b do not have any common factors. So we have a contradiction. From 6 we get that a and b have a common factor of 2, and from 1 we got our original assumption, we got a and b have no common factors. So we can finally say by contradiction of 1 and 6 are contradicting to each other, root 2 is irrational, meaning there's no two numbers a and b such that a divided by b is equal to root 2, where a, b are elements of the integers and b is not equal to 0. Hence proven. So there. This is one of the simplest methods to prove that root 2 is irrational. Thank you for watching.